Well, welcome everyone to another TCS Plus talk. We're really excited today to have Justin Gilmer from Google, who's going to tell us about a constant lower bound for the union closed sets conjecture. So before we get started, I do want to make a few announcements. First, it's really nice when people have their cameras on. It gives Justin some visual feedback. And please feel free to unmute yourself and ask any questions. But this talk is being recorded, but if you want to just stick around after the talk and hang out, there'll be an unrecorded session where we can just hang out with Justin and ask him all the questions that we don't want recorded. But in any case, so in 2 weeks, want to advertise also for Paul Goltz, who's giving a talk at TCS Plus. And then finally, let me thank the rest of the organizers. It's a big team in order to keep TCS Plus up and running. It includes Clement Kanan, Rachel Cummings, Anindya Day, Sumega Garg, Gautam Kamath, Ilya Rajenstein, Oded Ragev, Salil Shram, Noah Stevens Davidowitz, Tomas Vidik, and David Weitz. But with that being said, I'll hand the floor off to Justin. Please take it away.
Okay. Yeah, thanks for having me. So this talk is about the recent progress on Frankl's conjecture. So just to introduce the problem, so Peter Frankl in 1979 made the following conjecture that if you have any union closed family of sets with one exception, the family containing just the empty set, but for any union closed family except for that exception, there is an element that is in at least half of the member sets of the family. And so what union closed means here is that for any pair of sets in our family, the union is also in the family. So let's just make sure we understand the problem. We'll give an example. So this is an example I took from a survey paper on the topic. This is a union closed family, and I guess for any pair of sets here, you can check that their union is also in the family. So here I've just highlighted two sets, the set 4, 5 and the set 2, 4, 6. Their union is the green set 2, 4, 5, 6. And yeah, I mean, you have to check for all pairs that their union is in the family, but that holds. So that's the hypothesis. So we have a family that's union closed. And the conjecture is that there's an abundant element, which means that there's an element that's in at least half of the sets. So in this example, the element 4 would be in an abundant element, and it's contained in more than half of the sets. Actually, it's in 16 over 25 of the sets. Okay, so that's the conjecture that Peter Frankl made, and it's a wonderful problem. Probably one of my favorite problems from grad school. And so in this talk, we won't prove Frankl's conjecture, but we'll prove the first constant lower bound. So in this talk, we'll sketch a proof of the theorem that not that there's an abundant element, but that there's an element that's contained in at least 1% of the sets in F. And I guess the techniques introduced here, so we now know, I guess Frankl's conjecture holds for like something like 38.2 something percent of the sets. So we've been inching up towards 50%, but we're not quite there yet. And the proof uses information theoretic techniques, in particular Shannon entropy. Yeah, so but yeah, I guess before we get into the proof and the outline of the talk, let me just say something about myself. So yeah, I guess my PhD was in combinatorics. I graduated in 2015, and the last math paper I actually wrote was back in 2015. And I mean, I work at Google now. I do machine learning research. I still have a very academic job, but I'm no longer actively thinking about combinatorics. So you might wonder, why am I here giving this talk? So the story is, back in October last year, I was in New York for a friend's wedding, and I decided to drive down to visit my PhD advisor, Mike Sachs. We had a great lunch, and he told me about the textbook that he's working on, but we didn't really talk about math or anything. And I guess after this lunch, I decided to take a walk around Rutgers, and I was just reminiscing about my time in grad school, and what popped in my head but the union closed sets conjecture. I think if there were any problem that would have popped in my head, it would be this one. It was one of my personal favorites. Um, and but I didn't I wasn't trying to prove it or anything on this walk. I was more just recalling it. And I don't know, something weird happened on this walk, which is that I saw the problem completely differently than I had in grad school. So I spent probably 4 months on it in grad school, made zero progress, and somehow on this walk I saw the problem just completely differently. So I'll in this talk I'll sort of sketch what was I thinking about on this walk. But this eureka moment, we'll talk about what it was, but it had nothing to do with entropy or Shannon entropy. It was actually much more basic. And it really took like 2 weeks from this initial insight, working on it, where I formulated two conjectures. I'll tell you what they were. And I guess one of these conjectures turned out to be false. And it was really refuting this conjecture that led me to think about entropy. So yeah, I guess after coming up with this counterexample, I was able to formulate a better conjecture which used entropy, and that's how we got to where we are today. And so, the focus on this talk is actually going to be less about the proof, the final polished proof that's packaged all nicely in the paper. The talk's actually going to focus on the first initial 3 weeks, at least on my thought on the problem, and what sort of the thinking I did that sort of built the intuition, which eventually led to the proof. So this talk actually, the majority of the talk is actually not contained in the paper. It's not published anywhere. And I chose to do this because, one, I've always wondered, when I see a proof that sort of comes out of the blue, I've always wondered, how did that person think of that? And this is my one opportunity to actually tell people how did I think of that. So yeah, so if you're looking for a detailed explanation of every step of the proof, this is not the talk for you. This talk is again more about what sort of led to the development of the proof. Okay, yeah, so let me talk a little bit about just sort of what made this problem notorious, and sort of what were standard approaches to the problem previously. So one of the things that, I guess, if you've worked on the union closed conjecture, one of the things you probably know is that it seems like, I guess, what people often talk about is that every natural strengthening of the union closed conjecture is false. Meaning, we're trying to prove that there's this abundant element, but maybe try to prove something stronger. Like maybe the average, if I pick an element at random from a universe, maybe on average that element has abundance at least 1/2. And this would be an example of a false strengthening. You can see a construction here. This is a family F with 5 sets in it. And here the average element abundance is strictly less than 1/2. And the reason is because we sort of tacked on all of these. We have this gigantic set here, the set 1, 2, 3 up to 11. And the elements 3, 4, 5, 6, 7 all the way up to 11 seem to be kind of useless. They're not doing anything other than killing the fact that the average, these elements do nothing except for making the average abundance less than 1/2. And I guess a lot of my thought in grad school was trying to understand, well, what is special about the elements 1 and 2? And it's really not clear from this family, what is special about the elements 1 and 2 versus the elements 3, 4, 5, other than the elements 1 and 2 are in more sets than the elements 3, 4, 5. But that's what we're trying to show. So that's one of the struggles with this problem. You could really like, or yeah, so, and yeah, I guess I'm not the only one that sort of has struggled with this. I think Gil Kalai summed it up well, which is that, it seems like every counterexample or every meaningful strengthening, has a counterexample, and he argues actually that, or Jeff Kahn argues that he has a counterexample to every meaningful strengthening, and indeed he has many. So, yeah, I mean, I think in grad school, like, I spent a lot of time, just thinking about the normal direction, assume union closed, we'd like to prove there's an abundant element. And, there's just so much you can try. The problem is like completely open-ended. There's like lots of proofs of induction that you could imagine. There's lots of averaging arguments you could imagine. So averaging arguments are like, instead of trying to prove there exists an abundant element, let's try to define a distribution over elements that, if we sample an element according to this distribution, on average, the abundance is big. And I spent a lot, that was my personal favorite line of attack in grad school, was averaging arguments, trying to come up with the distribution and ultimate, but it's been very difficult. There's also like set system operations, and you're sort of asking, you're asking two questions, what is the structure of union closed families? And you're also asking, what are the special elements? And so, what was this eureka moment on this walk that I had? Well, honestly, it was to consider the contrapositive. So, the contrapositive, I've sort of written it symbolically here. It's so we're going to assume that we have a family that for every element I, it's not contained in many sets. So like for every element I, the probability that if I choose a set randomly that that the set contains I, that's less than some small number p. So you can think of p as like 1/1 billion here. And under that assumption, we'd like to show that this family is not union closed. Okay, so even today, I'm still scratching my head why I never thought about the contrapositive before, and I come to the conclusion that it's just ugly. It's hard to imagine a proof that ends with therefore F is not union closed. But on this walk, I wasn't trying to prove it. I was just happy to play with it in my mind, and the something interesting happens once you ask the question, like, okay, let's forget about union closed, but let's just study families that, families of sets that have small element abundance. And I'll pause here for any questions. I can't see people, so you'll have to like, someone will have to like verbally tell me if there's a question, but I'll pause here. Okay, maybe, anyway, please interrupt me if there's a question. Okay, so here's the first thought on this walk. So, suppose in the most extreme case, I guess the smallest abundance is, 1/size of F, meaning that there's another way of writing that every element is contained in at most one set in F. And if you consider such a family and look at the following construction, which I've written as F union F, which is, this is not the normal union operation. This is, you basically consider all pairwise unions. So I take all pairs A and B in my family and I consider their union. Then at least in this extreme case where every element's contained in at most one sets, then basically for every pair of sets in my family, I get a new union. And so actually, yeah, so this is not the normal union operation, anyway, so the observation is that, the number of unions you get when you take all pairwise unions grows like quadratically in the size of the family. So here's an example down here. This is a family with max abundance at most 1/size of F, meaning it's just a bunch of pairwise disjoint sets. And if we take F union F, or basically all pairwise unions, we get all the sets up here. There's 10 sets I've written here. You could include the diagonal terms like the set 1, 2, but I guess for this purpose, we just think about the A and B distinct. But anyway, the point is you start with a very sparse family, you took all pairwise unions, and you got many more sets than you started with. Okay, so that's an observation. So here's the second example. So suppose we, okay, I guess I've used this diagram to denote the power set, but suppose that we take all subsets of some small size. So we take some small p, and we take all sets of size p times n. So this is another sparse family. And when we consider F union F, we basically get all sets of size between p and 2 times p, or sorry, p times n and 2 times p times n. And again, this, I guess when p is small, the number of unions you get is much bigger than the family you started with. And in fact, as p tends to 0, the number of unions you get will grow quadratically again, relative to the size of F. Okay, so that led to this conjecture. So the conjecture was that there exists a constant p bigger 0 and a constant c bigger than 1 with the following property. If F is a family of sets where each element is contained in most p times sets in F, then the number of pairwise unions I get is grows as some like size of F to some power c. So I guess, of course, if you wanted to prove something about the union closed conjecture, like C, you just need like the number of unions to be size of F plus 1. But it seemed in like the examples that we just discussed that actually you get some polynomial growth in the number of pairwise unions. Okay, and so that was the conjecture I had on my walk. And I kind of liked it for a couple reasons. One is I remembered how hard it was to find interesting elements, and I kind of like this formulation because we're no longer trying to find some interesting element I, where we can actually just count how many unions we get. And so that seemed like at least very different from anything I had done in grad school on the problem. And the other reason why I liked it is, if you consider like trying to prove a normal direction, trying to prove that the normal direction, like assume union close, prove there's an abundant element, you might have a proof that looks like the following. You might pick some minimal set in F. You might consider the subfamily you get, which is like A union B for every B in F. And the problem with this proof is that this proof has barely used the union closed assumption. So this construction F sub A is, you're only touching linearly number of pairs A union B. Whereas like in this conjecture, where sort of by construction, we're considering all, size of F choose 2 pairs, A and B. And we're just counting how many sets we get. So that was why at least on this walk, I thought this was interesting. But on the walk, I didn't really think much of it. Actually, my main question was like, well, how have I never seen this before? Surely it must be false. It didn't like occur to me that I could have a new insight on this problem on an hour-long walk, especially given I hadn't like thought about math for 7 years. But I checked the polymath project. So there was in 2016, if you don't know, there was a polymath project on this problem on Tim Gower's blog, and a big group of mathematicians got together to work on this. And I actually just I was hoping to find a counterexample to this conjectural one I had, really so I could like get the problem out of my head and move on with my life. But when I went on the blog, I just basically did Control F, and despite many people working on it for several days, no one mentioned the fact that this problem has a contrapositive. And it's actually kind of interesting to go back and read the blog, because you can see a lot of the like normal kind of approaches where, maybe you're trying to prove by induction, maybe you're trying to come up with averaging arguments. But yeah, I don't know. I don't think I'm alone in being surprised that no one conjectured this like size of F union F grows. I don't, having talked to people, I don't think I'm the only one that's surprised that this conjecture one was sort of hiding in plain sight. But yeah, I don't know, something about this problem, I think we all forgot there was a contrapositive. Anyway, so I'll pause here. Is there questions or?
Yeah, I had a question.
Yeah.
So was there anything known, or did people ever consider like trying to prove this bound for a smaller p than half?
Oh yeah. I mean, that I think for a long time, yes. In fact, on the blog, the first post on the polymath project was, let's try to prove a constant lower bound. Like, let's try to prove there's an element that's in actually 1% of the sets. Yes.
But was there any subconstant bound known? Anything?
Oh, good. Yeah. The previous best known bound was it's like there's an element that's in at least 1 over log of size of F sets, fraction of the sets. So this, you have a, right, so it's 1 over log of size of F, which tends, that tends to 0 as size of F gets big. Thanks. Okay, but any other questions? Okay, so, all right, so I guess that gave me some confidence that this was new, but I really had no idea how to use this assumption. Like, we have a family where each element's contained in at most, p times size of F sets in F, and I didn't know how to use that assumption. And so I tried a different conjecture. I sort of replaced this assumption with the weaker assumption. So I had this conjecture 2 where that there exists a constant p bigger than 0 and a constant c bigger than 1. And I guess this conjecture 2, all I've done is, instead of assuming that, I guess, each element is contained in at most p times size of F sets, we're going to consider basically the average pairwise intersection. So we're going to compute this double expectation where, so you have to imagine we're sampling A and B uniformly at random from F, and we're computing the size of A intersect B divided by the size of A. And we're assuming that, I guess, on average, if I take 2 random sets A and B in my family, that their intersection is small relative to the size of A. So this is a, I guess, weaker assumption. I think the assumption that every element's contained in most p sets implies the assumption that this expectation is small. So this is a stronger conjecture 2 relative to conjecture 1. Okay, but this conjecture 2 is false, and really refuting it was really informative for me. So I wanted to share the construction in this talk and to explain how that led to thinking about entropy. But maybe I'll pause. Is there any questions about this statement, conjecture 2? Okay, good. So yeah, and I guess pictorially, like, the way to think about it is, we pick 2 random sets A and B, and we're just assuming that their intersection is small relative to the size of A. But this is in expectation. Okay, so here's the construction that refuted it. We're going to start with our universe is going to be this x1 union x2 up to x sub d, and then there are also these b's, b sub 1, b sub 2, You can ignore the b's for now. Like right now, just think about, we have x1, x2 up to xd. These are all sets, disjoint sets. And we're going to start with our family. We're going to start with the power set of each of these xi. So we start with, we have the power set of x1, we have the power set of x2, and all the way up to the power set of xd. So my final family is not going to have these sets. I'm going to start with this, and we're going to massage these sets in a way to before we get to our final family. So the way I modify these sets is, so let's take some a and x1, and we're going to like tack on a bunch of elements to a. So we're going to replace it with a union x2, union x3, all the way up to xd. And then we're going to tack on this b1. And so, yeah, so I guess we attach all of the rest of the elements in all the other xi's. And then we also tack on this gigantic set b1. So you should think about like b1 is huge. All of the xi's are much smaller and have the same size. But I guess the size of the xi's is also quite big relative to d, the number of xi's. Okay, so yeah, I do this for every a that's in x1. I add all these elements, and I guess I add the same b1 to every a. Right. So I do the same thing for. Oh, sorry. Yeah. I guess this animation didn't work very well, but yeah, just this b1 is we have the same b1 for every a. But then I guess in x2 we do the same thing. We take a b in x2 and we replace it with x1, union x3, or sorry, we add the elements x1 and the elements in x3 all the way up to xd, and we tack on this new b2, and b2 is disjoint from b1 and also is gigantic, and it's the same b2 for everything in x2. Okay, and I do the same thing for x3. There's a b3 that's used for everything there, and so on. Any questions about the construction so far?
Justin, so the B and the B actually have nothing to do with each other, right? Just
Yeah, that's an
unfortunate
unfortunate.
accident.
Yeah, that's an unfortunate
Okay,
notation
thanks.
collision. Thank you. Yeah. Good. Okay. So the first observation is that so if you take any a that's in x1 and then or any a that's associated with a set in x1 and any b that's in something associated to x2, and you take their union, you get the same union because all pairs a and b, their union maps to the same set, which is just x1 union x2 all the way up to xd, and then also the gigantic sets b1 and b2. And so you can start to see how this is sort of an interesting construction relative to what we're trying to show, which is that right now we have many pairs of sets which when we take their union, they map to the same set. And so this is sort of violating the intuition that we had, that maybe the number of unions I get grows. So this is one way that many sets can union to the same place. And in fact, this will hold for any pair. If you have a in xi and b in some xj that's different than I, then the same property holds. All their unions map to the same set. Good. And so I guess the final to get the final family F, we're going to basically take the union closure of this. So in my final F, we'll get d times size of xi sets, and then from the union closure, we're going to add this 2 to the d sets. And the 2 to the d comes from, like, you basically need, there's basically the power set of all the which B do you have? So there's like, yeah, so that's where the 2 to the D comes from, is that, but anyway, I'll pause for questions if this construction makes sense.
Aren't you supposed to have the 2 to the power xi? I'm confused. Why is it xi?
Oh, good. Yeah, it should be 2 to the power xi. Thank you. Yeah, good. Thanks. Yeah, so this should be d times 2 to the power xi plus 2 to the d. But I guess the main point is that this 2 to the d is very small relative to the 2 to the xi. And so when we take the union closure, we don't add many sets. You know, so if you imagine picking a random A and B, it's very likely to look like the above picture, where you're not picking one of these like 2 to the D sets that we added. You're going to very likely pick some A that's in some xi and some B that's in some xj, where I is not equal to j. That's sort of like the typical pair that we take. Okay, any other questions on the construction? Okay, so let's check that this quantity is small. So I guess if you imagine taking like a you know, random pair A and B, you know, in the event that you got some A that's in xi and some B that's in some disjoint xj, their intersection is going to be small because of these I guess because of these gigantic BIs that we tacked on. So this, you know, it sort of, we hit this like problem that you often hit when you think about the union closed conjecture, which is that if you try to define a strengthening, you know, you can construct a family and make these uninteresting elements appear that sort of like kill your strengthening. And that's sort of exactly what happened here, where this denominator size of A is very large, like artificially large, because of these B sub I. Yeah, so this expectation will be, you know, will tend to 0, I guess, as I think this expectation is roughly like 1 over d, because the main event, the main terms that contribute to the expectation are when A and B are in the same xi. Okay, so this is small, and it's also union closed, so the number of unions I get doesn't grow. And so, yeah, so I was staring at this construction, and I had 2 questions. So one is, what differentiates the interesting elements from the uninteresting elements? And 2, why did the number of, you know, when I took F union F, why did I not get many sets? Like, I thought that, yeah, yeah, the intuition was that, like, you know, you have size F, choose 2 possible unions, and there's no way to like cram all those, you know, cram all those pairs into this to some linear number of sets without reusing many elements. So I guess there are 2 observations. So the first observation is that, you know, so obviously the interesting elements are the elements in the xi. The b's are not interesting, but what makes them interesting is that they're the reason why this family has entropy. Like the reason why we have sets at all is sets need to disagree on elements. And, you know, I guess these xi's are where most of the I guess disagreement happens. So if you and, you know, so if you think about like sampling A randomly from your family and computing the entropy of A, you know, most of the entropy is like the elements in these xi's are contributing to the entropy of H of A. So that was the first observation. And, you know, and I guess the other observation is that all the interesting elements are contained in most sets. So, you know, and that's because we, like, you know, we replace this B in X2 with B union X1 all the way up to XD. So yeah, I guess most of the yeah, this family sort of like really grossly violates the like every element is sparse, because the elements in Xi are in like some 1 minus 1 over D sets. Okay, any questions on this?
Yeah, are you going to define entropy of A?
So this is Shannon entropy. I guess I apologize. I am assuming some familiarity with Shannon entropy in this talk, but you can think about it as like H of A is sort of quantifying the number of sets in this case. So I guess if you're unfamiliar with H of A, like
No. I mean, what's the distribution? I'm not quite sure what I
oh,
understand.
A is we're sampling A uniformly from our family, and
Okay.
so H of A is just what is it? It's like log of the size of F, right? So
okay, thank you.
Yeah, good. The reason why sorry.
It's not the A shown above. It's again, this is an unfortunate notation.
Yeah,
right?
Fortunate notation collision. You'll have to forgive me. I haven't given a math talk in like 7 years, so but yeah. So the intuition is you're like yeah, you're sampling an A uniformly at random from our family, and yeah, the reason why that random variable has entropy is because of the elements in the Xi. The B's don't really contribute to the entropy at all. Okay, and yeah, and actually, if A is sampled uniformly at random from F, and B is also sampled IID from F, then the entropy of A union B is going to be very small, because with the most likely event is this picture where A is in some Xi, B is in some Xj, and their union is going to collapse to the sort of only entropy in the union is just which Bi and Bj do you see. Okay, and so I guess that led to this final conjecture, which is now a theorem. So that's so there exists a constant p bigger than 0 with the following property. So we're going to sample A and B from, I guess, any distribution over subsets of n, and we're going to assume that just for every element I, that the probability that I is contained in A is at most p. And then we're going to assume this entropy is bigger than 0. And then I guess, yeah, the theorem is that under this assumption, the entropy of A union B must grow relative to the entropy of A. Okay, and so sort of before we were trying to show that the number of pairwise unions we get grows, so that we've replaced that now with the entropy of this random variable is going to grow. I guess the entropy of A union B. Okay, so just to give an example, so here's some family F. It's somewhat sparse, and we're going to associate sets in this family with just binary strings in the usual way. So I guess if the element I is in my family, then I'll write a 1, otherwise I'll write a 0. And yeah, so the assumption is that this binary string is sparse, meaning the probability of a 1 in any position is small. Yeah, so, and we're sampling A and B in IID uniformly at random. And we're computing A union B, which in terms of binary strings, they just take the bitwise OR. Okay, and then yeah, so then we're trying to show that the entropy is going to grow. The entropy of A union B is going to grow relative to entropy of A under these assumptions. Okay, so just let's just take an example. So one example is, suppose that each A sub I is IID Bernoulli with probability P. So this is more general than like sampling uniformly from some family F. This is like this distribution has support the entire Boolean cube, but it's sort of, you're very likely to sample a set of size roughly p times n, which I've drawn down here, which is the red line. So you're very likely to sample some set that's near the red line. And you know, A union B, if you know A and B are IAD, then their union is going to have size roughly like 2p minus p squared times n. And so the h of A and B is going to be oh, this is wrong. Sorry. Yeah, good. So h of A should not be p times n. It should be h of p times n. And h of A and B should be h of 2p minus p squared times n. I apologize for that. But yeah, I guess the point is that you know, when p is small, the entropy of h of A and B is going to grow. And I guess there's a point at which they don't grow anymore. So that's pictorially what I've drawn here. And to find this magic p that where the entropy of A and B doesn't grow anymore, you know, you have to solve this, you know, quadratic, but it's basically 3 minus square root 5 over 2. So this theorem, you can't prove this theorem for any p bigger than that special number. And I guess we now know this theorem for p is 3 minus root 5 over 2, thanks to the follow-up work. Okay, so I have just 2 minutes left. So let me at least convince you that this implies a constant lower bound for the union closed conjecture. And I can say a few words just about how the proof works. Okay, so yeah, so I guess to prove the constant lower bound for the union closed conjecture, assuming this theorem, so you know, assume that A and B are sampled uniformly from some union closed F, then it must hold that h of A and B is less than or equal to h of A. So this holds because, you know, the sort of max entropy distribution over some set is just the uniform distribution. And so h of A, or A union B, is just another distribution over our family. And so so yeah, the entropy of A union B can't be bigger than h of A. You know, but I guess this implies our theorem, because if we had a union closed family where every element's in at most 1% of the sets, then this theorem 1, you know, implies that the entropy must grow. So this is a contradiction. Cool. And so I'm out of time. I can like sketch the proof sort of offline if people have questions, but yeah, this is what I want to share. So
your theorem 2 is true even for 0.38, right?
Yeah. And so now, so yeah, I didn't prove it for, I proved it for 1%. I got stuck on, you basically get stuck on this kind of messy analysis question involving the entropy function. But there were, let's see if I have the timeline. Yeah, so yeah, I guess, so I proved it for 1% on November 16th. And, you know, I guess within a couple of days, we had like 4 independent groups showed this 0.38197. Yeah, Peabody was slightly later, but yeah, there's 4 independent groups that proved it for this special P. But I guess Will Sawin on November 21st sketched an argument for going just slightly past this special P. And so he, you know, he's basically considering like A, B, like sampling A, then sample B independent of A, and then sample some C that's coupled with A. And this coupling argument, he was able to push just past this number, but he didn't quantify it. And so there was some follow-up work. The first one's from you, who sort of quantified Will Sawin's epsilon to this just above this point, you know, it's just above 0.382. And yeah, I guess on December 26th, Canby tacked on a couple of extra digits. And I think Canby also argues that Will-Solin, that this is the limit of Will-Solin's coupling argument. Okay, but yeah, that's where we are today.
So did you say that Canby argues that this is the limit to which this technique can be pushed?
At least Will-Solin's coupling argument. So there's still many like ways you can sample A and B. Like maybe you like so yeah, Canby's argument only applies to very specifically how Solin sampled A, B, and C. But there's many possible ways that you could sample sets from your distribution that I think there's, I think that's where people are still trying to push, is like trying to come up with better ways to sample A and B and possibly a third set C. Yeah, other questions?
All right, well, I guess let's thank Justin for a wonderful talk. But yeah, we'll open the floor up for questions.
So is this an Erdős problem?
So not really. So I mean, I don't know the full history, but I've talked a bit with Peter Frankl, and so my understanding is that, so Peter Frankl made this conjecture in 1979. It was in a paper that he wrote, and he shared it with some colleagues. And he was a young mathematician at the time, not well known, and it kind of went viral, this conjecture he made. So his colleagues shared it with their colleagues, and people in conferences would share with each other. And this is before the internet, so I guess it went as viral as something could back in that day. But it quickly spread. But what happened was, within a few years, like if you're working in combinatorics, you had probably heard of the problem, but you didn't know who conjectured it. This game of telephone didn't benefit Peter Frankl. And so I think there are some mathematicians who thought it was sort of a folklore conjecture, or maybe an Erdős problem, but it seems like Erdős didn't know about it before Peter Frankl. So I don't know if Erdős, I don't think Erdős assigned a monetary value to it or something. So
yeah, that's what I was asking.
Thanks.
I didn't mean to imply that Erdős was the first person to pose this conjecture, right. But I was wondering as to whether Erdős associated a money value with this.
I don't think he did. Which is unfortunate. I think it's I think it's deserving of it. I think it's a great conjecture. Cool. Other questions?
Okay, well, I mean, as promised, I can take us off the recording.